Hello everyone, welcome to our webinar. I'm Aylin. I'm working at Mavili Electronics Academy department, and today we are going to talk about detection via linear cable type heat detectors. So the main purpose of fire detection systems is to protect lives, safeguard critical equipment, and manage risks without interrupting day-to-day operations by detecting a fire as early as possible. However, not every environment is clean, stable, or easily accessible enough for traditional point detectors, such as smoke or point heat detectors, to work reliably. In areas with high airflow, heavy dust or dirt, humidity or condensation, constantly changing temperatures, or where the risk extends over long distances, pinpoint detectors often trigger false alarms and require frequent maintenance. And this is exactly where the cable-type heat detection systems become a much more practical and reliable solution. So as the name implies, cable-type heat detectors are fire detection systems that monitor an entire line rather than a single point, allowing them to detect temperature increases anywhere along the cable. In these systems, the cable itself acts as the sensing element. The cable is installed along the area where the risk exists, and when the temperature exceeds a predefined limit, it sends an alarm signal to the fire alarm system. This means the system can respond much closer to the source of the fire and much faster, especially in long or extended areas where the fire risk is spread out. As a result, cable-type heat detection offers major advantages in terms of life safety, protection of critical infrastructure, and maintaining uninterrupted operations. In transportation infrastructures, cable-type heat detectors play a vital role in ensuring both safety and uninterrupted operations. Metro lines, rail system tunnels such as Marmaray, and station connection tunnels are long and hard to access areas where intervention can be challenging. In these environments, where a fire can spread within minutes, early detection, reliable alarm signaling, and precise identification of the fire location are critical operational requirements. Similarly, in large-scale facilities like airports, the use of heat detection cables in terminal service areas, baggage handling systems, cable shafts, and technical rooms is considered a strategic solution not only for fire safety but also for maintaining the continuous operation of essential systems. So, one of the key reasons for choosing cable-type heat detectors is their ability to provide targeted detection in hard-to-reach areas. In environments such as tunnels, air movement, exhaust effects, and airborne pollutants can be significantly reduce the effectiveness of smoke detection. In addition, if the exact location of a fire inside a tunnel cannot be identified quickly, response efforts may be delayed. And linear heat detection systems offer a strong advantage in tunnel applications as they can monitor long distances continuously and in some solutions pinpoint the fire location with meter-level accuracy. Similarly, in industrial facilities such as refineries, process areas, tank farms, and production lines, fire risk often begins not with open flames, but with overheating. Detecting abnormal temperature rises in electrical equipment, motors, bearings, conveyor belts, and power distribution points at an early stage makes it possible to intervene before a fire develops. In these harsh industrial environments, detection systems are expected to be reliable, resistant to challenging conditions, and free from nuisance alarms. For this reason, cable-type heat detection is widely preferred in process and infrastructure areas where heat-related risks are high. Another major application area for cable-type heat detectors is cable galleries, tunnels, and cable trays. In these environments, the main fire risk comes from the heating of cable insulation caused by continuous power transmission and the close or dense arrangements of cables. A fire that develops along cable routes can lead not only to localized damage, but also to cascading failures that may result in a complete shutdown of operations in large facilities or critical infrastructure. Although fire detection and alarm systems have been used in tunnels since the 1960s, several major accidents in Europe between 1999 and 2001 clearly demonstrated their critical importance. For many years, however, the widespread installation of these systems was approached with caution, mainly due to the belief that conventional fire detection devices, while capable of early detection, were also prone to false alarms. Recent advancements in detection technologies have changed this perception. Modern tunnel fire detection systems now offer early detection, low false alarm rates, and advanced emergency management capabilities, making them more reliable and effective for tunnel applications. For a long time, linear heat detection systems based on copper tube technology were considered the primary solution for the fire detection in tunnels. In recent years, this approach has been complemented by a range of new technologies, including cable-type heat detectors with sensors at fixed intervals, in other words, point indicating systems, fiber optic sensing cables, non-point indicating linear heat detection cables, camera-based smoke detection systems, in other words, video analysis, and air sampling smoke detectors and flame detectors. So as you can see in the table 1, it compares the different systems and methods used to detect fire-related effects inside tunnels. An evaluation of these tables shows that cable-type heat detectors with sensors at fixed intervals stand out in terms of fast fire detection, low false alarm rates, and wide detection coverage. In addition, their ease of installation and virtually maintenance-free operation have made them one of the most preferred tunnel detection solutions in recent years. In tunnel applications, it is generally expected that a typical car fire be detected within 60 seconds under airflow conditions of 10 meters per second. From this perspective, cable-type heat detectors offer a clear advantage by providing early and reliable detection. Due to their extremely low false alarm risk, these detectors can be directly integrated into the automatic control of ventilation, smoke management, and emergency announcement systems. In contrast, most smoke detection systems primarily provide information to operators, and critical systems are activated manually only after operator confirmation. Linear cable-type heat detectors are made up of sensors installed at predefined intervals within a specially manufactured, flame-retardant, and halogen-free cable. These sensors are arranged consecutively along the cable, forming a continuous linear detection system. For each detector, both fixed heat alarm thresholds and rate of rise alarm thresholds can be configured independently. In addition, pre-alarm levels for both threshold types can be individually adjusted, allowing for early warnings before a full alarm condition occurs. The measurement interval of the control unit, as well as how frequently the reference temperature value is automatically updated, can also be configured to suit the application. The system includes temperature measurement and addressing circuits placed at specific points along the cable. Measurement and address data are transmitted to the connected fire alarm control panel, enabling precise monitoring. and the detectors can measure ambient temperature with an accuracy of up to 0.5 centigrade degree. Typical examples include heavy industrial facilities, cold storage and refrigeration areas, as well as power plants and solar energy systems. So, the linear cable type heat detector is composed of sensors installed at predefined intervals within a specially manufactured, flame retardant and halogen-free cable, as I said before. And the system consists of a control and evaluation unit and a sensor cable that contains the heat sensors. The sensor cable can be connected either directly to control unit or via a junction box using a dedicated connection cable, and termination elements are used to properly terminate the sensor lines. This detector is immune to environmental influences such as humidity, smoke, dust, vibration, icing, abrasion, and electromagnetic interference, enabling reliable operation even under harsh conditions. And thanks to this robustness, it delivers highly stable performance in installation galleries and similar demanding environments. The control unit communicates with intelligent addressable fire alarm control panels via Modbus over the RS-232 protocol. Sensors spacing can be freely selected depending on the application, and branched cable installations are supported. Since each heat sensor has a fixed address, the exact physical location of every sensor along the cable can be precisely identified. All heat sensors within the linear cable are recognized as individual input devices by the fire alarm control panels. As a result, standard input device parameters such as event type, zone, location name, and use in cause and effect scenarios can be fully defined for linear cable type heat detectors. In conclusion, the design and implementation of fire detection and warning systems based on cable type heat detectors provide an ideal solution for early fire detection in road and railway tunnels, heavy industrial facilities, power plants, and solar energy systems, cable galleries, vertical cable shafts, cold storage facilities, and explosive environments. Although many products on the market are referred to as cable-type heat detectors, fire detection systems, especially in tunnel applications, should be designed using solutions that offer effective rate of rise detection performance and fully comply with the EN 5422 standard. So that's all for today. Thank you for your participation. See you next week at 11 a.m. and you can watch the video on our YouTube channel.